move on to the instrumentation amplifier. So the instrumentation amplifier is a very, very important application of the op-amp. It is used even today in almost all industries. Whatever the type of industry, whenever you need to use some kind of control, you need to measure some parameter at some place where maybe it's not possible for a human to go. Say it's a power plant or some kind of processing where a human can't intervene. There are very high, large variations of temperature, or there can be lots of increase or decrease in pressure, something like that. So in lots of industry plants or power plants, industry places where different parameters need to be measured at that point, and based on that result, based on the measurement, you need to control the operation. You need to have some kind of control of the operation of that plant, or say it's a furnace, it's a boiler, anything. You need to measure the temperature. If the temperature goes beyond 100 degrees, you need to switch on a coolant. And say if the temperature comes below 60 degrees, maybe you need to switch on the heater, or you need to add some coal. You need to build in the fire to heat the furnace. So something like that. You need to keep measuring and monitoring different units in industries. Then the best way it can be done is using this instrumentation amplifier. It is used even today. It's a simple kind of sensor where the instrumentation amplifier would be used in almost all industrial places. Okay. So what is this application of op-amp as an instrumentation amplifier? So this op-amp as instrumentation amplifier has three important blocks. The first one is called the input stage. The second block is called the intermediate stage, and the last block is called the output stage. So you have input stage, intermediate stage, and the output stage. And whatever is the physical quantity which has to be measured. So you have some physical quantity like temperature, pressure, whatever. That physical quantity will be connected as input to the first stage, that is input stage. And what is this input stage consist of? It consists of a transducer along with a preamplifier. So what is a transducer? Can someone tell me what's a transducer? A transducer is a circuit wherein it will convert a signal from one form to another, basically from physical to electrical voltage or current, or from an electrical voltage or current back to a physical parameter. So what is a physical parameter? A physical parameter can be something like temperature, pressure, all those are physical parameters. You measure the temperature, but I need to convert that temperature to an electrical quantity so that I'll be able to understand and send back a control signal and process it. You should be able to process this electrical parameter. So you can see here the physical quantity or parameter. I think Maruti, you can switch off your video. Yeah. So the physical quantity to be measured will be connected as input to the transducer, and there is a preamplifier also present in this input stage. So what does this preamplifier do? At the site, wherever I am placing this transducer, remember transducer will be a device like a thermistor. For example, if I have to measure the temperature in the furnace or boiler, I'll place a thermistor, which is a temperature sensitive resistor, right? I'll place a sensor like a thermistor at that place, and whatever is a sensed temperature, that should be converted to an electrical voltage or current, and then it should be passed on to the next amplifier stage. But what happens if I directly send it? The value of voltage, the converted level of voltage or current will be so small. It will be in milli or microvolts that by the time it travels through a wire and reaches a central processing unit or a central processing place, it would have got merged with noise. Lots of noise will be added to the signal as it travels. So even from the place where the temperature is measured, from the furnace to the central control room or somewhere, through a wire, if it has to travel, noise would get added because the signal is very small in amplitude. So since the signal is too small in amplitude, it would be merged with noise and it would be very difficult to separate out the signal from noise. Okay. So what we do, along with the transducer, the measuring device. So I have a device like a transducer, which is nothing but a sensor used to measure some physical quantity. And I place this sensor at the point where I need to measure. Okay. And at the same place, I will have a small amplifier added, a pre-amplifier we call it as. So one small stage of amplification is done at that point itself. That is to enhance the magnitude. So as I told you, if the converted temperature will be in millivolts, when it is converted to electrical voltage, it will be in millivolts. You amplify it to the range of few volts. You do a small amplification and then pass it on through the wire to reach the central processing unit, which is a control room. Okay. So then the addition of noise will not affect the signal more. Is it clear? So the input stage consists of a transducer which takes in a physical quantity like temperature, pressure, something, converts it to an electrical voltage or current, and it also has a small amplifier, a pre-amplifier, which amplifies that converted voltage or current to a little larger value so that it can be passed on to the next stage. Now we have transmission lines here which will pass on the signal measured and converted. The electrical voltage or current which we get here after measurement and conversion and amplification, it is passed on through transmission lines or wires to the next stage. This stage is usually present in a central control room. In the industry, usually there will be a control room where we are going to do this processing. So the intermediate stage is basically our instrumentation amplifier. So the instrumentation amplifier which we are going to study now usually will form the instrumentation, the intermediate stage. And here we are going to give high amount of amplification and we will minimize the noise. So the main advantage of an instrumentation amplifier is its very large voltage gain and very low noise. Noise in the sense CMRR. Any signal which appears in common to both the input terminals. All of you remember what is CMRR? So whatever signal appears in common at both the input terminals, it is a common mode signal. So that common mode signal should be rejected completely, rejected effectively. That job is done well by this instrumentation amplifier. So please understand the instrumentation amplifier has three main advantages. First thing, very, very high gain. It can be designed to get a very high gain in thousands. So few thousands I can get the gain easily, and you can get a variable gain from minimum of 1 to maximum of a few thousand. That's the first advantage. Second advantage, it has a very high CMRR in the sense any signal which appears in common at both the input terminals will be effectively rejected. So if the CMRR value of the amplifier is high, it can reject noise signals effectively. Remember, noise signals will appear in common at both the input terminals. So they can be effectively rejected. And last thing is it has a very high input impedance because we use non-inverting stages in the beginning. So I'll show you the circuit diagram. So the third important point which you should remember in an instrumentation amplifier is its what? Very high input impedance. So very high gain, very high CMRR, very high input impedance and low output impedance. So these are the important properties of an instrumentation amplifier, because of which they designed this whole amplifier as an IC. And today we have instrumentation amplifier IC readily available, like our simple 741. We have IC 725 and all, which are instrumentation amplifiers. And they will be very useful in all your project works. I don't know how many of you would have tried some mini projects. Wherever you need some better amplifiers, we'll use the IC version of the op-amp instrumentation amplifier. That's the best one which can be used for amplification. Okay. It rejects noise, or it reduces noise, and it gives you very high gain also. So, and controlled gain. You can control the complete gain from minimum to maximum by using a resistor. Is it clear? All that is possible. Now, once the amplification or the processing is done in this intermediate stage, we pass on this signal through again transmission lines, you can see, to the output stage. So what this output stage will consist? It will usually consist of some kind of indicator, a measuring device, a meter, or it can be a controller. So if it's used in a process control plant or in a factory, it will have a controller. Based on that output value, you will take some action like switch on the fan, send the coolant, or switch on the heater, something like that. So some kind of control action can be done based on the measured value. So this whole system is called an instrumentation system. An instrumentation system will consist of a physical quantity like temperature, pressure, which would be measured by using an input stage which has a transducer and a preamplifier. The output of this transducer and amplifier will be an electrical voltage which is passed through transmission lines through to an intermediate stage which has an instrumentation amplifier. This instrumentation amplifier will give you very high gain, very high CMRR and high input impedance, low output impedance. So this circuit gives us the required gain for the signal, and then the value will be measured using a meter or an indicator output stage. And if based on the value some control action needs to be taken, that would be done here. So this is a simple instrumentation amplifier. So as I told you, so another example for a transducer is a strain gauge. All of you would have worked with strain gauge in your physics lab. So what happens in a strain gauge? When you apply pressure to the strain gauge, there will be a change in its resistance. And that resistance change can be converted to an electrical current or voltage if I place that strain gauge in a Wheatstone's bridge or something. So a simple example of another transducer is a strain gauge, which is used for pressure measurement. So as I told you, instrumentation amplifier provides very high amplification, high CMRR, high slew rate. Hope you remember what is slew rate. Slew rate is a measure of change in output voltage with respect to time. So it is a measure of the speed of response of the op-amp. How fast an op-amp output can change based on change in its input. So especially when you give a square wave, there is a sudden change in the input. We want the output to change immediately. So for example, if you change the input suddenly like this and give such an input to this op-amp, we want the output of the op-amp to also change as fast, but usually it will change a little slowly. Though it is a sudden change in input, the output may change a bit slowly. That's because it needs some time to respond to a change in input. Okay. So slew rate is a measure of the speed of response of an op-amp. And this instrumentation amplifier will also give us a high speed of response or a high slew rate. And output stage uses meters, oscilloscopes, any indicators. Transmission lines, as we know, permit transfer of the signal from one unit to the next unit, and especially it is needed when the transducer is present at a remote site. I told you in almost all industries that is needed. Okay. Next, we'll consider the actual circuit, which is an instrumentation amplifier using a transducer's bridge. So this is the actual circuit which we are going to consider here. In this case, we have a Wheatstone's bridge network initially, and there are 4 resistors in this Wheatstone's bridge network: RA, RB, RC, and the 4th one is a thermistor or a resistive transducer. You can see it is RT plus or minus delta R. Can you see the value of this circled resistance? It is showing RT, the basic value. The base value is RT. So that base value will be fixed at some temperature. Say for example, at 25 degrees centigrade, I'll say the value of this RT is 100 kilo ohms. But if temperature increases above 25 degrees, the value of resistance will increase. Or if temperature decreases, the value can decrease. Or it can be the reverse also. Okay. So what you need to remember, this resistance value changes whenever the temperature changes. So it is called a resistive transducer, and basically it is a thermistor. So how do I indicate the value of a thermistor? RT base value plus or minus delta R, because it's going to change in resistance. And you can see this bridge is excited by a DC voltage VDC between these 2 points, and the output should be measured between the opposite 2 points. If I excite the bridge between here and here, say I call this as, for example, I'll call this as C and this as D. So I'm connecting the excitation between points C and D, and this point is A and this is B. I'll be measuring the output voltage between the points A and, so this is A and this is B. Okay. So between these 2 points, you can see the output is measured, and since we are measuring the voltage at this point as VA and the voltage at this point as VB, the combined effective voltage in between this and this point can be called VAB. So how do you find VAB? It is VA minus VB. Okay. So VAB is the voltage from point A to point B, the output of the Wheatstone's bridge network. The input to the Wheatstone's bridge network is this DC voltage, VDC, which is connected between points C and D. And output is taken between points A and B, and the difference in the voltage measured in between these 2 points is VAB, VA minus VB. Okay. So this is what is measured, as you can see. Now we have to calculate the output voltage of this bridge network. And as you can see, first part is your what? Input stage. So this whole thing is the input stage, which has a sensor like a thermistor, and that sensor measured value, the temperature value, should be converted to a voltage, for which I'm going to use a transducer like a Wheatstone's bridge. So I have a complete Wheatstone's bridge network, and I will place this sensor or thermistor in one arm of the Wheatstone's bridge, and whenever temperature changes and this resistance changes, the Wheatstone's bridge output voltage will change, and that output voltage will be passed on to the instrumentation amplifier, which is the intermediate or the middle stage. So as you can see here, this whole thing is your instrumentation amplifier, the intermediate stage what we saw. Okay, and what does it consist of? It has two. What circuit is this? What is this circuit? Inverting terminal shorted to the output, input given to the non-inverting terminal. It is a simple voltage follower. Yes or no? So this is one voltage follower. This is the second voltage follower. We make use of two voltage followers to which we give the differential input from the Wheatstone's bridge. So output of the bridge is fed to the two voltage follower circuits. And what is the second stage? What is the stage? We have done this. R1, RF, R2 is equal to R1, R3 is equal to RF. What is this circuit? This circuit is nothing but a, please unmute and answer. I'll at least know you are there or not. What stage is this? This is a differential circuit or a difference amplifier where one input is given here, the other input here, or I can give a differential input VAB in between these two terminals. You remember we did this difference circuit in yesterday's class only. Okay. So this is a simple difference amplifier where we give the difference voltage in between these two terminals. And from where will I get that difference voltage? I'm using voltage followers in the initial stage. So you can think, why voltage follower? Actually, this is a simplified version of instrumentation amplifier. I'll show you in the end another version of instrumentation amplifier where we are going to use non-inverting amplifiers in the first stage. Instead of voltage followers, we can use two non-inverting amplifiers. Why we can do that? When I want high gain, here all the gain should be provided only by this differential stage. The second stage of the instrumentation amplifier, which is a differential stage, only this circuit. What is the gain of this circuit? RF by R1. Yes or no? When I take this resistance is equal to this resistance, R1 is equal to R2 and RF is equal to R3. When you equate these two and these two, what is the combined gain of this stage? The combined gain of this stage will just be RF by R1 into whatever is the differential voltage which is given. Whatever is the voltage which is connected here, if I call this voltage as say VOB, for example, this one, or VO2, and this as VO1, output of op-amp 1. So I'll get the final output of this V0 is VO2 minus VO1, where VO2 is the output of this stage and VO1 is the output of A1 stage. So you have the input to the differential stage as VO2 and VO1. Output will be RF by R1 into VO2 minus VO1. We have seen all this. So please understand here, we are working the instrumentation amplifier using two voltage followers and one difference amplifier stage. So these two combined is acting like instrumentation amplifier here, and any gain that is provided by the instrumentation amplifier is only the gain provided by the second stage or the differential stage. This voltage follower will not give us any gain. But if we want to design this instrumentation amplifier to get very high gain, then I can simply replace these voltage followers with a non-inverting amplifiers. I'll use two non-inverting amplifiers here instead of voltage followers. It will give you much higher gain than this type of connection. Anyway, in our textbook, this is the connection given. So we will analyze this. So input stage has a thermistor or a resistive transducer, which forms one arm of the Wheatstone's bridge network. The other three resistors are RA, RB, RC, and I can measure the output of the Wheatstone's bridge when I give an excitement of VDC, a DC voltage to 2 points in the bridge. The opposite 2 points, I'm going to measure the output voltage VA minus VB or VAB. This is fed to two voltage follower circuits, which is the first part of the instrumentation amplifier, and the same VAB will come here. Then you can ask me why you need it. Can somebody tell me? I'm giving the input VAB here and I'm getting the output same. I'm using voltage follower, right? So I'm feeding a voltage VA here and VB here. So the difference between VA and VB, VA minus VB is VAB. I told you. You're giving this and getting the same output. What is the point in connecting this? Yes? Please respond. At least put a message. Put a message in the chat, no? Yes?
For impedance matching, ma'am.
Impedance matching, or because a non-inverting stage or a voltage follower gives you very high input impedance, naturally it will what? Help in preventing any loading effect. There won't be a loading effect or reduction in this signal. If I don't use this voltage follower, the signal VAB will be much reduced by the circuitry by the time it, even if it gets connected directly to this difference stage, the second stage. So if I want to avoid that, for impedance matching, as you told, this voltage follower stage should be used, and it also gives a very high input impedance to this instrumentation amplifier. Okay, so this is the circuit of instrumentation amplifier. The output stage you can see is a indicator like a meter. I have used a meter where a resistance change is shown as a reading in the meter. It can be indicated, or the voltage change will be represented here. Usually it's the output voltage which is connected to this meter. So you can have a simple voltmeter which will indicate any changes in voltage. So this is our instrumentation amplifier circuit. Now let's, as I told you, what is RT? All this is told. The bridge is DC excited, but you can give AC signal also here. If required, I can connect an AC excitation also. Now, initially in the analysis, we consider the bridge should be balanced initially, and it should be balanced at some reference condition. And what is that reference condition? That reference condition tells us at certain temperature, say I'll take room temperature as the reference, and usually we consider room temperature as 25 or 27 degrees centigrade. So at a reference temperature, whatever is the resistance of the thermistor, we choose the same resistances for these three also. So what happens? This bridge will be in balanced condition, or the output of the bridge will be zero. Whenever the Wheatstone's bridge is in balance, output from the bridge is zero. We know that. In balance condition, output from one point, VA, will be equal to the output voltage from the other point. In the sense, VA minus VB will be zero. If I say this, VA is equal to VB, which means VA minus VB or VAB is zero. The bridge is in balance condition, and that balance condition is chosen at some reference temperature. Okay. So what is the value of VA in this circuit? What is this voltage VA? It can be taken as the voltage across this resistance RA, right? And if I consider this branch, RT plus delta R and RA, what is the excitation voltage? VDC. So VDC is fed. It is like, sorry. So it's a connection like this, VDC, RT, RA, and I am interested in finding this voltage VA, and this is grounded. Correct? I am taking only this arm, this and this. If I take this arm, I have an excitement signal VDC or a connection. This is my RT plus or minus delta R, and this is RA, this resistance. So what's the voltage VA? VA is the voltage from this point to ground. Use the voltage divider rule. VDC into RA by RA plus RT plus or minus delta R. Yes or no? So what is the voltage VA across this resistor? VDC into RA by RT plus RA, or RA plus, what is this RT? I have a plus or minus delta R here. So that would be the voltage VA. Similarly, can you tell me what will be the voltage if I consider this arm? VDC is the excitement. I am interested in finding the voltage VB at this point. From this point to ground, the voltage is VB. So what would be the value of this voltage? It is the voltage across this resistance, RB. VDC into RB by RB plus RC. Yes or no? So the value of this voltage VB would be VDC into RB by RC plus RB. The same thing we have written in the next page. So I have just considered what is the value of the voltages VA and VB. So you can see VA is VDC into RA by RA plus RT. We are considering that there is a fixed base resistance RT at the reference temperature of 27 degrees or something. The value of the thermistor resistance is RT. So that's why I left out that plus or minus delta R. And this is RB. VB is RB into VDC by RB plus RC. VA is RA into VDC by RA plus RT. Now, if I simplify this, I'll get this condition. And I think we are all familiar with the condition of bridge balance in Wheatstone's bridge. The ratio of the resistor RC by RB will be equal to the ratio of the resistor in the other arm. So, the resistor in the top divided by resistor at the bottom is equal to the resistor at the top divided by resistor at the bottom in the other branch. So, this is the condition for bridge balance in a Wheatstone's bridge. We got this condition. Now, generally, the resistors are selected so that they are equal in value to the transducer resistance RT. I told you that. So, usually what we'll do, we'll select RA, RB, RC all equal to RT, say at a fixed temperature of 27 degrees centigrade. All of you just send in your USNs into the chat with your sections. I think we have some 4 minutes left, after which we will log in back to the session. So just send your USNs now. Now, I was telling you, usually what we do to get, rather than choosing these two ratios to be equal, in the sense, rather than trying to make RC equal to RT and RB equal to RA, we will take all the 4 resistors equal. And to what value? To that base value of the thermistor resistance, which is what? Determined at the room temperature. So the reference condition what we state here is the room temperature. At room temperature, whatever is the value of the thermistor resistance, that is RT. Okay. So usually we choose this condition. And then, so reference condition is the value of the physical quantity under measurement when the bridge is balanced. So the bridge is balanced at room temperature. If the temperature increases above the room temperature, the bridge will be imbalanced. If the temperature goes below the room temperature, the bridge will be imbalanced. Why so? Because this thermistor resistance changes. We said this plus or minus delta R comes into picture when the temperature changes. When temperature is room temperature, it will be just RT. When temperature increases or decreases, this plus or minus delta R will be added to this RT. So when one of the resistances changes, the balance condition of the bridge is lost and we will have some output voltage. When bridge is balanced, VA is equal to VB, output voltage VAB is 0. When bridge is imbalanced, the output voltage will not be 0. Please remember that. So, the value is normally established, as I told you, based on some simple characteristics. So,